Today, we will talk about the Machmeter. However, before going into detail with this instrument, let's remember what is the Mach number. The Mach number is the ratio between the aircraft's true airspeed and the local speed of sound, which is abbreviated as LSS. Therefore, the Mach number is equal to the true airspeed divided by the local speed of sound. So for example, if this aircraft is flying with a true airspeed of 438 knots and the local speed of sound is 638 knots, to obtain the Mach number we just have to take 438 and divide it by 638. This way, the current Mach number of this aircraft is 0.68. In other words, this means that the aircraft is flying at 68% of the speed of sound. Now, if in this case the aircraft accelerates to, for example, 523 knots, then the Mach number increases to 0.82, which means that it is flying now at 82% of the speed of sound. In this order of ideas, if the aircraft flies exactly at the speed of sound, in this case 638 knots, it will be flying at Mach 1, or in other words, at 100% the speed of sound. But we might be wondering, why is it important to know the Mach number? Well, the thing is that as an aircraft approaches the speed of sound, the airflow over certain parts of the aircraft can reach Mach 1, thus generating a shockwave, as we can see in this example. Here, this aircraft is actually flying at Mach 0.82, which means that the aircraft as such has not yet reached the speed of sound. However, despite this, the airflow in some parts of the aircraft can accelerate and reach Mach 1, as in this case over the wing. Now, in these situations, aircraft that are not designed for supersonic flight will experience certain negative effects, such as an increase in drag, high-speed buffet, Mach tuck, and reduced effectiveness of flight controls. So, in order to avoid these adverse effects, it is important to know the exact speed at which the shockwaves start to appear. The speed at which this happens is known as the critical Mach number. And it is defined as the Mach number at which the airflow over any part of the aircraft reaches the speed of sound, or in other words, reaches Mach 1. Let's look at the following example. This aircraft is flying at Mach 0.81, which is below the speed of sound. However, if we look at the airfoil, we will see that even though it is moving through the air at Mach 0.81, the airflow over the wing is accelerated and reaches Mach 1, and therefore a shockwave will develop there. So, with this in mind we can say that in this particular aircraft, Mach 0.81 is the critical Mach number. This implies that below Mach 0.81, all the airflow around the aircraft will be subsonic, or in other words, below the speed of sound. And above Mach 0.81, there will be supersonic flow in some part of the aircraft, and therefore also shockwaves. So taking into account this critical Mach number, the manufacturer establishes a maximum Mach number for operation, which is abbreviated as MMO. This constitutes the limitation to the Mach number at which the aircraft can safely fly. Usually in subsonic aircraft, this MMO has a certain safety margin with respect to the critical Mach number in order to prevent the aircraft from getting too close to that speed. In this particular example, this aircraft has a critical Mach number of 0.82. This means that if the aircraft flies above this speed, shockwaves will start to appear, and with them, all the related adverse effects. So, in order to avoid the aircraft from getting too close to that limit, the manufacturer sets Mach 0.75 as the maximum Mach number for operation. This way, there is a safety margin with respect to the critical Mach number. Now, it is important to mention that the Mach number cannot be directly related to any other speed indication, since as we have seen, this Mach number depends on the true airspeed and the local speed of sound, both of which change depending on the conditions. So, with this in mind, let's first look at the relationship between the true airspeed and the Mach number. As we already know, as the altitude increases, the air density decreases. This results in an increase in the true airspeed in relation to the indicated airspeed. And as we have already mentioned in previous videos, the true airspeed increases by approximately 2% for every 1,000 feet increase in altitude. And as we can see in the Mach number formula, if the true airspeed increases, the Mach number also increases. Which means that the aircraft gets closer to its maximum Mach number for operation. Let's now see the relationship between the local speed of sound and the Mach number. As we know, as altitude increases, the air temperature decreases. And this results in a reduction in the local speed of sound, since it is directly related to air temperature as we can see in this formula. Now, looking again at the Mach number formula, we can see that the speed of sound is inversely proportional to the Mach number. This means, in other words, that if the speed of sound decreases, the Mach number increases. And therefore the aircraft gets closer to the maximum Mach number for operation. These effects caused by the increase in altitude result in a condition known as coffin corner. Let's look at it more in detail with this graph of altitude versus true airspeed. As we know, the stall speed of an aircraft is a constant indicated airspeed. However, since true airspeed increases with altitude, the stall speed expressed in true airspeed actually increases. On the other hand, the reduction of air temperature with altitude causes the local speed of sound to reduce as well. This will cause the MMO expressed in true airspeed to reduce with altitude. So as we can see, this results in a narrow operating range at the top of the graph, which is known as the coffin corner. If an aircraft operates under this condition, if it accelerates it will exceed the maximum Mach number, while if it decelerates it will stall. With this we can say that at high altitudes, the speed range at which the aircraft can operate is considerably restricted, as we can see in these examples. So having seen all this theory, it is clear that it is important to have an instrument on board that indicates the current Mach number of the aircraft. And that instrument is the Machmeter. This instrument can have different presentations. We can find it as an individual analog instrument or incorporate it in other instruments or systems. Let's first look at the analog Machmeter. This instrument uses the relationship between dynamic pressure and static pressure to determine the current Mach number. This means that this is a pitted static instrument. But we might be wondering, why does this instrument use static and dynamic pressure if the Mach number is related to the true airspeed and the speed of sound? Well, to understand this, we have to look at the relationship between the dynamic and static pressure and the Mach number. Let's start with the dynamic pressure formula. As we can see, the dynamic pressure is directly proportional to the air density and the true airspeed. And if we rearrange the formula to obtain the true airspeed, we will see that in simple terms, the true airspeed is proportional to the dynamic pressure divided by the air density. Having seen this, let's now move on to the static pressure. As we already know, if the static pressure increases, the air density also increases. And on the other hand, if the static air temperature increases, the air density decreases. So in other words, we can say that the air density is proportional to the static pressure divided by the air temperature. If in this case we rearrange the formula like this, we can see that the air temperature is proportional to the static pressure divided by the air density. And as we will recall, the local speed of sound is directly proportional to the air temperature. So then we can say that the local speed of sound is proportional to the static pressure divided by the air density. Now, taking into account these two statements, we can relate them to the original formula of Mach number. We just replace the terms, and we obtain this other formula. Here we cancel out the air density, and we obtain that the Mach number is proportional to the dynamic pressure divided by the static pressure. That's why the Machmeter can use these pressures to determine the Mach number. Having seen all this theory, let's now see how does the analog Machmeter actually work. This instrument receives information from the pitot tube and the static port. And inside the case it incorporates an expansion diaphragm, such as the one found in a regular airspeed indicator, since it allows us to measure the dynamic pressure. And on the other hand it also incorporates an aneroid capsule, such as the one found in an altimeter, since it allows us to measure the static pressure. These capsules are interconnected by means of gears that in turn move the needle on the instrument's dial. Let's take a closer look at how this instrument would work internally. Here, the static port is directly connected to the instrument case, while the pitot tube is connected to an expansion diaphragm, which in turn is connected to gears. This part of the instrument would work as a regular airspeed indicator. The static pressure would enter through the static line, while the total pressure would enter through the pitot line. In this case the total pressure would try to expand the diaphragm, while the static pressure would try to compress it. However, as we know, the total pressure is equal to dynamic pressure plus static pressure. Which means that in this case, the static pressure inside and outside the diaphragm is the same, so they cancel each other out, leaving only the dynamic pressure. In other words, the diaphragm will only expand and contract depending on the dynamic pressure changes. Now, this instrument also incorporates an aneroid capsule, which is sealed with a constant pressure inside of 2992 inches of mercury. This way, this pressure inside the capsule would try to expand it, while the static pressure outside would try to compress it. And since the pressure inside the capsule is constant, it will only expand and contract depending on static pressure changes. This way, having measured both the dynamic and static pressures, the gears of the instrument can relate both values to determine and indicate the current Mach number of the aircraft. Now, this was a simple explanation of the basic principle of operation of the instrument. Since in reality, it looks like this on the inside. It may seem complex, but all it does is relate the dynamic and static pressures to determine the Mach number. The instrument in the cockpit is really simple and easy to read. It consists of a needle and the Mach number scale, although in most cases the scale also incorporates a marking that identifies the MMO of the aircraft. Now, as in any other pitot static instrument, the Mach meter also suffers from some indication errors. Here we can highlight the instrument error, which is caused by small manufacturing imperfections and gear wear of the instrument. And there is also the position error, which is caused by errors in the pressure measurement due to maneuvers or changes in aircraft configuration. This means that under certain conditions, the dynamic and static pressure measurement is not completely correct. Now, as a side note here, the Mach meter does not suffer from air density and compressibility errors, as these cancel each other out due to the principle of operation of the instrument. On the other hand, the Mach meter reading is also affected when the pitot tube or the static port get blocked. Let's look at the pitot tube blockage first. As we know, the pitot tube has a main intake hole and also a drain hole at the rear. Due to this design, different types of blockages may occur. Specifically, there are three possible cases: a main intake blockage, a drain hole blockage, and a blockage of both holes. In each one of these cases, the Mach meter will react in a different way. So let's see each one in detail, starting with the main intake blockage. In this case, the dynamic pressure can no longer enter the tube, and therefore, the residual dynamic pressure in the tube will escape through the drain hole, thus leaving only the static pressure. This makes the Mach number reading drop to zero, just like in a regular airspeed indicator. Now, on the other hand, if there is a drain hole blockage, the total pressure continues to enter the tube through the main intake hole. So we can say that the Mach number reading will be relatively normal. However, one thing to keep in mind is that water can accumulate inside the tube, which may lead to large measurement errors over time. Now, let's look at the last case, where we have both holes blocked. In this case, the total air pressure no longer enters the tube, but also, the pressure inside the tube cannot escape either. This way, the pressure trapped in the system will give a false Mach number reading. Here, as long as the aircraft maintains altitude, the Mach meter will freeze, indicating the last Mach number measured before the blockage. On the other hand, if the aircraft climbs or descends, the instrument will act as if it were an altimeter. This means that if the aircraft climbs, the Mach number indication will increase. And if the aircraft descends, the Mach number indication will decrease. Now, in case the static port gets blocked, the Mach number indication will not be affected as long as the aircraft maintains altitude. But if the aircraft climbs or descends, the instrument will act in the opposite way of an altimeter. This means that if the aircraft climbs, the Mach number indication will decrease. And if the aircraft descends, the indication will increase. Up to this point, we have already seen the analog individual Mach meter, which is common in older aircraft. However, in more modern aircraft it is common to find the Mach meter together with other speed indicating instruments, such as the regular airspeed indicator. So, to compact both speed indicating instruments into one, the IAS Mach indicator was developed. However, one important thing to mention regarding this system is that the Mach meter operation no longer relies on the pitot static system, but is fed by the air data computer, which is abbreviated as ADC. Let's see what is an air data computer. Basically, this is a processing unit which receives raw data from the pitot static system and the total air temperature probe. This means that this computer receives information about the total pressure from the pitot tube, static pressure from the static port, and total air temperature from the corresponding temperature probe. Then, the unit processes this information and directly calculates various relevant parameters that are sent electronically to the instruments in the cockpit. Normally these parameters are altitude, indicated airspeed, vertical speed, static air temperature, true airspeed, local speed of sound, and finally, the Mach number. But how exactly does the computer calculate the actual Mach number based on the received information? Well, initially the ADC calculates directly the values of the static air temperature and true airspeed. With this information, the unit can determine the local speed of sound and then apply the original formula to obtain the Mach number, as we can see. Now, we might be wondering, why is it important to integrate the Machmeter with the regular airspeed indicator? Well, although these speeds do not have a direct relationship, it is important to take both into account during operation, especially at high altitudes. But let's see why. At low altitudes, the speed is limited mainly by structural issues, which means that the maximum speed is expressed in terms of indicated airspeed. However, at high altitudes, speed is limited mainly by the adverse effects of shock waves, which means that the maximum speed in this case is expressed in terms of Mach number. We can understand this more easily by means of this graph of altitude versus indicated airspeed. In this case, the maximum indicated airspeed for operation remains constant with altitude. However, the maximum Mach number for operation, expressed in terms of indicated airspeed, actually reduces with altitude. Therefore, here we can see the operating envelopes. The green area represents the speed range in which the aircraft can safely operate, while the red area represents the speed range in which the aircraft has exceeded one of the speed limitations. So as we can see in the lower part of the graph, at low altitudes, the aircraft speed is limited by the indicated airspeed limitation. While at higher altitudes, it is limited by the Mach number limitation. The altitude at which the change in limitation occurs is known as the changeover altitude. So, it is clear then that the crew must take into account both limitations in order to safely operate the aircraft. Let's look at this during the climb operation. Initially, the climb is made with a constant indicated airspeed until the aircraft reaches the changeover altitude, where the climb is continued with a constant Mach number. Let's look at this with this graph. Here we have the applicable speed limitations, and the behavior of the airspeed during the climb would be as follows. As we can see, below 10,000 feet, the speed is normally limited to 250 knots due to regulatory constraints. Then, above 10,000 feet, the aircraft accelerates to a constant indicated airspeed, in this particular example, 300 knots. The aircraft continues to climb with this airspeed until it reaches the changeover altitude, where it is not possible to continue the climb with a constant indicated airspeed, since the maximum Mach number would be exceeded. So in this case, the aircraft must continue the climb with a constant Mach number, which in this case is Mach 0.78. This behavior of the speed during the climb is known as the speed schedule, which in this particular case would be 250, 300, Mach 0.78. And during the descent we have exactly the same situation, but in reverse. Initially the descent is started with a constant Mach number until the changeover altitude is reached, where the descent is continued with a constant indicated airspeed. Here we have the same graph, so in this case the descent would start with Mach 0.78 until the changeover altitude is reached. Then it is continued with a constant indicated airspeed of 300 knots until 10,000 feet, and finally the speed is limited to 250 knots due to regulatory issues. Therefore, the descent speed schedule in this case would be Mach 0.78, 300, 250. So, having understood the importance of relating the indicated airspeed to the Mach number, let us now look at the parts of the instrument. This is pretty similar to a regular airspeed indicator, however it incorporates the Mach number indication. We can also see the analog indicated airspeed scale, along with a numerical indicator. There is also the indicating needle and an additional needle known as the barber's pole, which will indicate the current speed limit of the aircraft. Let's see how this barber's pole needle works. Basically it consists of a moving needle with red and white stripes, which indicates the maximum operating speed of the aircraft at a given time. Now, since at low altitudes the speed is limited by the VMO, which has a fixed value, then the needle will remain fixed, indicating that speed. However, at higher levels, above the changeover altitude, the speed is limited by the MMO, which decreases with altitude. In this case the needle automatically adjusts the speed limit according to the Mach number limitation. Let's see an example of this. Here we have the same graph of speed limitations. In this case we will assume that the VMO is 350 knots. Now, let's say that we are flying at a low altitude with an indicated airspeed of 300 knots. In this case we would get an indication like this. As we can see, the airspeed needle indicates 300 knots, while the barber's pole needle indicates the current speed limit of 350 knots. This will continue like this until the aircraft reaches the changeover altitude. From this point, the speed limit will gradually reduce due to the Mach number limitation. As this happens, the barber's pole needle will gradually move to indicate the current speed limit. So as we could see, this barber's pole is pretty useful to the pilot since it continuously indicates the maximum speed at which the aircraft can safely fly at a given moment. Now, so far we have seen how a conventional indicator works. However, we can also find this same principle of operation in digital instruments like this one. Here we can see the Mach number indication and the representation of the barber's pole. I hope the information presented in this video was useful. If so, don't forget to share, like, subscribe, and leave a comment down below. Thanks for watching.